Hi everyone! Today we're going to talk about how to find the dimensions of a cylinder that minimize its surface area. To complete this problem, we'll draw a picture of the problem and write what we know, identify optimization and constraint equations, and then use the derivative of the optimization equation to find the dimensions. Let's take a look. In this particular optimization problem, we've been told that a cylindrical can must be made to hold 1 liter of oil, and then we've been asked to find the dimensions of the can that will minimize the cost of the metal used to make it. As with any optimization problem, the first thing you want to do is draw a diagram of what you've been told and write down as much information as you can. So we've drawn a diagram of the cylinder and we've indicated R as the radius and H as the height of the cylinder. We've also written down that 1 liter is equal to 1,000 cubic centimeters and that the area formula for a cylinder is 2 pi RH plus 2 pi R squared. We also know that the volume of a cylinder is pi R squared H. So really quickly, in case you don't remember those, remember that the area formula is 2 pi R, which is the circumference of the circle, times H, the height of the can. So that gives you the outside, or the material used to make the side. And then pi R squared is the area of the circle, so that'll give you the top and bottom. You multiply by 2 to account for the top and bottom together. So when we simplify, we get 2 pi RH plus 2 pi R squared. The formula for the volume is the area of the circle times the height of the can. So the area of the base times the height, which will give us the total volume of the can. Once we've written down all the information that we've been given, our next step is to identify a constraint equation and an optimization equation. So with any optimization problem like this, you're always going to need an equation you can optimize, but you'll also need a constraint equation. Because we've been asked to minimize the cost of the metal, that means that we're going to be minimizing the surface area of the can because the metal is defined by the surface area. So minimizing the surface area means that our optimization equation will be the area equation. So let's go ahead and just say that this area equation here will be our optimization equation. Our constraint equation is the equation that limits us. So we've been told that the cylindrical can has to be made to hold 1 liter of oil. That's the only constraint we've been given. So what the problem is asking is for us to optimize the area, the surface area, minimize the cost of the metal or minimize the cost of the surface area within the constraint or within the condition that the volume has to hold 1 liter or 1,000 cubic centimeters. So this volume equation here will be our constraint equation. Our next step is to figure out how to reduce our optimization equation to just one variable. So because we have in our optimization equation here both R for the radius and H, we need to get rid of one of those. The way that we're going to get rid of one of them is by solving the constraint equation for one or the other and then plugging in to the optimization equation. So let's go ahead and solve our constraint equation, our volume equation, for either R squared or H. In this case, let's go ahead and solve it for H because that'll be really easy to plug in to the area equation. We've just got H right here. So the way that we'll do that is by plugging 1,000 cubic centimeters in for volume. We know that has to be the volume. And we'll set that equal to pi R squared H, and then we'll solve for H. Obviously, to solve for H, we'll just divide both sides by pi R squared. So we'll get 1,000 divided by pi R squared. Now that we've solved for H, we can go ahead and plug that back into our area equation. So if we say area over here is equal to 2 pi R multiplied by H, which we solved for as 1,000 over pi R squared, plus 2 pi R squared, now we have our optimization equation for surface area in the form of one variable, R. And now that we've got it in one variable, all we need to do is simplify, take the derivative, set the derivative equal to 0, and solve for R, and R should give us the radius of the can that minimizes the surface area. So let's go ahead and simplify this first. We'll see that we get pi to cancel here, and we'll get R to cancel from the numerator and the squared to cancel in the denominator. So we'll be left with just 2,000 divided by R plus 2 pi R squared. Let's go ahead, now we need to take the derivative because we've simplified this as much as possible. So let's go ahead and make this a little bit easier on ourselves. We'll call this 2000 r to the negative 1. Remember that we can move a variable from the denominator to the numerator just by changing the sign of the exponent from a positive to a negative. So 2000 r to the negative 1 plus 2 pi r squared. If you're not comfortable doing this, you can obviously use quotient rule to figure this out. So we're going to take the derivative, a prime, and we'll get negative 2000 r to the negative 2 plus 4 pi r. And when we move this r to the negative 2 back to the denominator, we'll get negative 2000. And actually, let's go ahead and make that our second term so we don't lead with a negative. We'll get 4 pi r minus 2000 over r squared. So that is our derivative equation. Now we need to set this equal to 0 and solve for r. So if we set it equal to 0, let's at the same time go ahead and find a common denominator. In order to find a common denominator, we're going to be multiplying this first term by r squared over r squared, and we'll get 4 pi r cubed. We can combine the fractions, minus 2000 all over r squared. So now what we can see is that this right-hand side here is going to be equal to 0 whenever the numerator is equal to 0 or if the denominator is undefined. However, if the denominator is undefined, that means r is equal to 0, and we know r can't be equal to 0 because we're talking about a three-dimensional figure here in real space, and if r is equal to 0, then the cylinder doesn't exist. So we can almost just discount that, and we're really just looking at where the numerator is equal to 0. So let's go ahead and factor out a 4, and we'll get 4 times pi r cubed minus 500. Obviously now we can see that the right-hand side will equal 0 only when pi r cubed minus 500 is equal to 0. So we can really just ignore the 4 or divide both sides by 4 and that'll go away. And now if we add 500 to both sides, we'll get 500 equals pi r cubed. If we divide both sides by pi, we'll get r cubed equals 500 divided by pi. And if we solve for r by taking the cube root of both sides, we'll get r equals the cube root of 500 divided by pi. We know now that this must be the radius that minimizes the surface area of the can. If we want to find the height as well, we can just go ahead and plug r into our height equation. It's not very clean, but we'll get 1000 divided by pi times, and now we have r squared here, so we get the cube root of 500 divided by pi, all squared. That's really just going to give us 1000 divided by pi times 500 over pi to the 2/3 power. So these are the dimensions h here and r here that minimize the surface area and therefore minimize the cost of the metal used to construct the can. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.